So this chapter looks a lot like instrumental analysis. So I know some of us don't like to take notes, but I strongly suggest it because this is just like instrumental, right? So this very first diagram, I just say know it, right? And when I say know it, I'm talking about, like, remember, like, rotation. Oh, what spectrum of the, what region of the electromagnetic spectrum was that? That's microwave, right? So know those relationships. And how they have some symbols on here that we should be aware of. Like here's cm with a -1. What is that? What do they call that? Inverse centimeters, yes, but what symbol? There was this one. It was wave number with little tilde on there, which is 1 over wavelength, right? And what was if you take the tilde away? Wavelength is lambda. This is wavelength. Frequency. So the energy of a photon was h nu, or h, right? hc over lambda. Okay. So just remember that kind of stuff, right? Because like here they're listed kind of like wavelength, wave number, frequency. Right? I'm just going by their units, because look at their units. That's what it has to be. Okay. Emission spectroscopy. So what was spectroscopy again, Ashley? Interaction between what and what? Bradley, light and matter. Yeah, he just took the exam, so that's all right. So emission. Which way am I going here? All right, energy's going. I shouldn't put my arrows in. It's going to confuse you. It's obvious. Ground state's E0, right? E1 is the first excited state. Emission, which I'm going from where to where? It's emission spectroscopy.
E1 to E2?
It's emission. E1 to E naught, right? Because I have to be emitting light. I'll be emitting E1 minus E0. Right? That'll be the absorption. Just go in the, just simply reverse what here, Pablo? It's absorption.
They'll be going up.
Yeah. Just draw the arrow up. Would be absorption. Dispersing element. So we're talking about spectroscopy here. Which instrument upstairs, name one of them, please, Mr. Rico, that has a dispersing element in it? See how good my art is. AA has a, yeah, AA has a dispersing element in it. What else does? GC. Help them out, somebody. See if you remember this stuff. UV vis. What is a dispersing element? IR does not have a dispersing element. Scatters the what? Now, scatter is kind of a misconception, though. That's not the word of choice, because scatter to me sounds random, right? Disperse, diffract is a much more controlled notion. So that's the word that I think you should use, even though it is really scattering. You're right. But it's diffraction in a very controlled manner. What do you use to do that? So it's the G. Grading. Right? So the black box with a dispersing element, we called that a, there's an M, Bradley.
The black box.
black box with a dispersing element in it. All these wavelengths come in. Only one wavelength comes out. Monochromator, right? Fourier transform. So if you have a dispersing element in your instrument, you're doing spectroscopy, which again, Pablo, is the interaction between light and matter. So we're doing spectroscopy. If your spectroscope has a dispersing element, you don't need to do the Fourier transform because you have a dispersing element. You have the individual wavelengths coming out, so you're interacting one wavelength at a time, and you can keep track of all this stuff, right? But if you do not have a dispersing element, you have to do the Fourier transform. In fact, what you need to build is a Mickelson Interferometer. Everyone in here has built a Mickelson Interferometer, right? Everyone's had that lab? So now you know what I'm talking about. They have these different mirrors and path lengths and things. So what they're going to do is there's no dispersing element. So all these wavelengths are coming in at the same time. Whether they're fast, long, short, they're all coming in, hitting your sample, right? Absorbing, doing that whole gambit. Okay, well what you're going to do is you're going to take that transmitted radiation and you're going to put it into a Mickelson interferometer and just have a little detector on the end and move one arm back and forth mechanically, physically. That mirror's moving back and forth. What's going to happen to this over here? Yeah, all these fringes are changing, right? So you're getting a changing in an intensity. So technically, don't let all this stuff throw you. I'm just doing what their conventional notation is for this stuff, G of omega. But really all that is intensity. And over here, they're moving the mechanical arm, right? They're moving one of the what in the Mickelson interferometer back and forth? One of the mirrors, right? That's all. So you change the interference pattern. So you're going to change the intensity. Okay. So this is what the signal looks like. Doesn't look at all like an absorbance spectrum, right? What frequencies are present? Well, it turns out if you do an inverse Fourier transform, you get your intensity, right, and your wavelength, or wave number, or frequency, whatever you computer wants to kick it out as, right? But in this case, it looks like there's only 3 wave numbers. So in this signal, there was only 3. So you can monitor their change, and here's your spectra. Okay, so there's no dispersing element, not necessary. Detector, I think we got an idea what that is. Raman, I like how they attach the word spectroscopy to Raman, because it is spectroscopy. It's scattering spectroscopy. It's light's coming in and it gets scattered. But the collision isn't elastic, it's if a collision isn't elastic, it must be inelastic. So these scattering occurrences are inelastic. Either the light is, the technical jargon is either the light is blue shifted or red shifted, right? So if the light is blue shifted, that means it gained or lost energy. Gained energy. If that light is scattered and it's red shifted, it lost energy. So that's the interaction between light and matter. So pretty much everything scatters radiation. So this type of spectroscopy is widely used. This is a detector on a lot of different instruments because everything scatters radiation. There's only a very few things that don't, and we'll talk about that. But okay, so you remember how IR, a lot of things are much more narrow. Okay, so that's what's powerful about it. So that's where this Stokes and anti-Stokes comes in. Stokes radiation, that's that scattered light that was actually red shifted, right? It lost energy. Anti-Stokes is that blue shifted scattered light. It actually gained energy. Okay, so that scatterer lost the energy then, right? Rayleigh, what's the difference between Rayleigh scattering and Raman scattering? If Raman scattering is inelastic, sorry, we said Raman is elastic, Rayleigh must be inelastic. Right? There's inelastic collisions. There's no red shifting or blue shifting, right? If blue light's is the incoming radiation, blue light is the outgoing radiation. Why was the sky blue? Because of what type of scattering? Rayleigh, because that nitrogen molecule is just the perfect size to scatter blue light. And it's Rayleigh because the blue light doesn't change color, right? Doesn't shift. Good. You guys remembering some stuff? Okay. Intensities of spectral lines. The Beer-Lambert law. Okay. These I's are what? Well, that is a symbol for I, but no. Intensity, right? So one of these is the incoming intensity. One of those is the incident. Which one is going to be the incident? The one with a little zero will be your incident intensity. Exactly. What's the units for intensity of light? You're close. Watts. Since we're in the metric system. I have no idea what it is in the Brit system, right? But it's watts. How about all these other things? Like in this Beer-Lambert law, the transmitted intensity is equal to the incident intensity times 10 to the power negative E, J in brackets, little l. What is this J in brackets probably? J in brackets. What do the brackets mean?
Oh, the species that's absorbing?
Yes, it's what? Concentration, right? You just think of the things, just imagine the things that are going to affect lowering the transmitted intensity. Concentration, definitely, right? How about that little L? The length of what? Yeah, the cuvette. They call it, the technical word is path length, but it's just the distance that the light's traveling through this medium. One left, little epsilon. It's this thing. Molar absorption coefficient. It's just how well this compound J absorbs at that wavelength. So one thing, I have never seen the Beer-Lambert law written the way I like to write it. Everything has to have a subscript lambda on it, except length and concentration, because that's not wavelength dependent. But they all need, this is one wavelength at a time, right? This is all wavelength dependent. Okay, and you can measure transmittance, just the transmitted over the incident. So the units would cancel out; it'd be unitless. You can take the log of both sides and rearrange and get the Beer-Lambert law in the way that I think we introduced it in instrumental. Maybe using different symbols. I think we used B for path length, but it's all there. Okay. Now we're getting into some more P-chemish stuff. Okay. And they're P-chemish because they make things sound more complicated than it is. Stimulated absorption. Well, we used to just say absorption. Okay. Now we're supposed to call it stimulated absorption. It's the exact same thing we've been talking about before, right? What were we talking about before? This. So nothing's really changed.
Well, did they just start doing that?
So stimulated absorption. Nothing's changed. It's absorption. But we're supposed to call it what absorption? Okay, now you're doing P-chem. The transition rate. Einstein got his mitts into this, right? For one molecule, what's its transition rate in going from the ground state to that first excited state, E0 to E1? That's omega. Okay, well, how do you get omega? You just multiply this magic number, your fudge factor, your Einstein coefficient of stimulated absorption for that molecule, all right, some constant, times little rho. And it makes sense because look at little rho, the energy density. Well, yeah, if light's more intense, it should be excited more often. Does that make sense? That's all energy density is, intensity of that incident light. So nothing really too complicated yet. So if this is for one molecule, how do you get the transition rate for all molecules? Just multiply the rate for one molecule times the number of molecules. So n would just be the total number of molecules. Okay.
And what's omega?
It's written up there. Transition rate for one molecule. So I like this diagram is pretty interesting because it explains this. It explains lasers. So we have absorption, right? Incoming light. So I'll just draw a little arrow in here. Incoming light, right? It gets absorbed. So you go from E0 to E1, right? Okay, now you're a molecule and you're in the excited state. So the rule is here, you can't do internal conversion. You have to actually emit light. So they're just talking about, this is assuming the only way to get to the ground state is to emit light. And you and I know that's not true. I mean, just heat's the numero uno way. But we're just talking about you have to be emitted. So there's two ways. One is just random. It just shoots right out of there, right? The photon's just emitted. Okay, and what photon is emitted? Again, it's E1 minus E0. That would be its energy. Okay. The other way is, hey, we're going to send in this photon of light. So this is something new. It's just passing by that molecule. And it stimulates the emission of that excited molecule. And since it stimulates it, look what happened. What changed? The A word. Amplitude. And there's now two photons here, because this was an incoming photon. Now you have two outgoing photons, but they are what? The C word. They are coherent. They're in phase. This is the beginning of a laser. Okay? So you have spontaneous emission versus stimulated emission. Stimulated emission is where you have to have an incoming photon, and it stimulates the emission. Okay, now the photon has to be just right? Because it has to match in energy, but it'll stimulate the emission. And then you'll have two photons coming out, and they're coherent. So that spontaneous emission as the Einstein coefficient A. And they're just showing you they're not showing you the big equation to calculate it. They're just showing that spontaneous emission is directly proportional to the frequency of light cubed. So it magnifies itself. So would you have more spontaneous emission, see if you're following this, in the IR or in the visible? Where would you have more spontaneous emission? If spontaneous is directly proportional to the frequency cubed. The visible, because which one has a higher frequency?
No,
Visible does, right? Because visible's higher energy is higher frequency. So visible will have more spontaneous emission, right, than IR would be. So it should be easier to make an IR laser than the laser in the visible. And it is. How about this? Roy G. Biv, the colors of the spectrum. Which color would be the easiest to make a laser of due to spontaneous emission? Red would be the easiest. Which one would be the most difficult? Which laser pointer is freaking expensive? Violet. And they just started making them like 7 years ago. And I paid like $500. Well, you paid $500 for that because I took it out of lab fees. So, but it's so cool. But it's really cool, right? Okay.
So, I'm sorry, I'm a little confused then. The higher energy is easier to have emissions, right? Emissions, spontaneous emissions, correct?
Mm-hmm. Do you want spontaneous emission for a laser?
No.
You want
Okay, I'm back on track.
You want stimulated emission. Good. That's a good point, though. I didn't bring it up very well. Einstein showed that, right? Okay, he showed some stuff. And if you want to calculate these Einstein coefficients, just look at the relationship. Okay? Just believe them. Gross selection rules. Just in general, what are the selection rules for this stuff? For example, the one that you know, or should know, is what has to happen for a molecule to absorb infrared radiation. It has to exhibit a what?
Frequency.
Well, they're all absorbing frequency. That's the whole point. Is it going to absorb an IR frequency or not? Will it absorb in the IR region? What has to happen? What has to be going on with that molecule? Now, IR's vibrations, yes. If you go back to that chart, it says vibrations. But what has to be going on during that vibration? Oscillating dipole, yes, ding, 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 right? Oscillating dipole. If you do not have an oscillating dipole, it can't absorb IR radiation. Can a nitrogen molecule absorb IR radiation? No, because it's nonpolar. No matter what vibration you do to try to break the symmetry, it's not going to work. So you can have a molecule that's nonpolar, carbon tetrachloride. So not all of its vibrational modes will absorb, remember? Only the vibrational modes that exhibit an oscillating dipole will absorb IR radiation. Okay. Let's see here. What are the other ones? Rotational transition. Molecule. Yes, you did know that. Molecule must be polar. You're the one who answered the question. How could you say you didn't know that? Molecule must be polar if you want to exhibit a rotational transition. So I don't think anyone's done the PChem lab with carbon monoxide.
No, we're all working out together.
Right? So carbon monoxide, is carbon monoxide polar? You have CO. Is that a polar molecule?
Yeah.
Most definitely, right? So this will exhibit a beautiful rotational spectrum, and that's why we picked it. Okay. So molecule has to be polar to exhibit rotational transitions. Rotational Raman transitions, name your kid this.
Raman?
No.
Oh.
This gross selection rule. Anisotropic polarizability. Anisotropic polarizability. Now remember, I was talking about how Raman is a fantastic detector because pretty much everything scatters radiation. So anisotropic polarizability must be something that, heck, most every molecule can exhibit. And all it is what's the difference? Well, hit the word polarizability first. Anything's polarizable, right? Because if you have incoming radiation, radiation is composed of what two fields? Magnetic and electric. Since we're talking about spectroscopy, which field are we almost always interested in? Electric. There's only one instrument up there that doesn't care about electric. Woohoo! All right? So this electric field, oscillating electric field, will cause what to oscillate in a molecule? Electrons. So that's inducing polarizability. So it's very easy to make molecules polar. Their polarizability. Everything has electrons, so everything does this. It's just that if you want to exhibit rotational Raman spectroscopy, it needs to be anisotropic polarizability. So that means you can't have a perfect, I mean, this molecule has to be perfect. So there's nothing different around it anywhere. Like a perfect sphere. That would be isotropic polarizability. Doesn't matter how that light approaches it, it polarizes it the same. That would be isotropic polarizability. So it's not going to work. But there's hardly anything in nature that's like that. So anisotropic polarizability is the key for rotational Raman spectroscopy. Line widths. In instrumental, we talked about how, like down here, especially in the AA, we have these transitions going from ground state to excited state, and it's a gas, so it should be a bloody single line, but they're not bloody single lines. They have some line width to them. And Doppler effect was a huge reason for this, right? That when these little sodium atoms, if you're looking at sodium light and you're supposed to see this one single line, well, this little sodium atom could be going towards the detector, or it could be going away from the detector when it emits the light, right? That's a Doppler effect. Remember when I was swinging what over my head and you could hear the Doppler effect? I didn't bring it in because I figured you'd remember it.
You were swinging something over your head.
And you heard the Doppler effect.
Is it a tuning fork or?
It was a speaker, right? So when the speaker was going towards you, you heard a higher pitch. When it was going away from you, you heard a lower pitch. Right? That was an instrumental. I thought you'd remember that one for sure, if anything. Okay, so that's the whole idea here. So if you have receding, so let's get this stuff here. Here's the observed frequency, right? V naught would just be, right, the frequency of that source. If it wasn't moving, right, can't be moving. You'd have to be the source itself to experience that. S would be the speed of the source, right? C is the speed of light. Because are we talking about Doppler effect with sound or Doppler effect with light here? Light. So C is the speed of light. S is the speed of the source. So it's plus, right? So we can actually decrease the frequency a little bit. If it's approaching, the frequency actually gets a little bit higher. So your denominator is a little bit smaller. So all you do is just subtract in the denominator instead of add. Okay. So when they're talking about line widths, here's their symbol for it. This is what they're talking about. To actual the right one, I didn't do it quite right. See what this height is and find exactly the midpoint. I guess the midpoint would be right around here. So my line width should be right there. That distance is my line width. Okay. Full width, half max is what they kind of call it. Okay, Doppler broadening continued. So now we're just throwing in the mass of, now we're talking about a distant star. And this little line is supposed to be at this wavelength because we see it right here on planet Earth. I mean, I'm looking at the spectrum, and this little, what's a element that would be in a star? This little iridium 77, right, whatever, it's supposed to emit right here. Well, here's iridium 77 and star XYZ, and it's shifted a little bit, right? So you can calculate really the temperature of that star is what you're really after, because you can measure all this other stuff. What's K in that equation? Who's constant? Starts with B. You did a lab on them. Boltzmann, right? M would be the mass of the little atom that we're talking about, right? Or isotope.
And T was what again?
Would be the temperature.
Oh, okay. Just want to make sure.
The temperature of that star, really the temperature of that atom we're talking about, but he's in the star, so it'd be the temperature of the star. Whatever the object is. right? So I'm just saying in a story. The temperature of M. Temperature of M.
Mass?
Mass of what?
This dark.
No, the
Universe.
Of the iridium 77.
Yeah, whatever's emitting the light. Okay, lifetime. If we had glow-in-the-dark toys in instrumental analysis, right? Their lifetime is on the order of milliseconds. It's just the average amount of time a molecule spends in the what state? Excited state before it
Goes to the
emits light and goes to the ground state. Yeah. Okay. So, and they're just saying that this is a Heisenberg uncertainty principle idea, that since you have a lifetime, you get broadening due to just lifetime broadening. You get a contribution to the line width. One is Doppler, the other one is lifetime. Okay, and you can calculate either one. Okay, and this is really due to the Heisenberg uncertainty principle, which is really kind of abstract for us because we never really messed with time-dependent Schrödinger equations or anything like that. So we just kind of got to take it on faith there, which is pretty much what all quantum mechanics is, but it seems to be working pretty good. What does this mean? Tau is our lifetime. What does the /PS mean? It means that this lifetime, if you want this to work out, had better, because see the approximate symbol? This lifetime, whatever you're going to plug in here, had better be in units of PS. What is PS? Pico. Yeah. And pico is 10 to the negative 12. Close. 10 to the negative 12. So you can calculate the lifetime. If a homework question starts talking about collision rates, just take 1 over the collision rate and you get the lifetime. Okay. So now they're talking about rotational spectra. So they kind of stopped everything here. And they said, hey, now we're going to talk about rotational spectra. All right. And you have moments of inertia. We kind of did this before, right? The distance, right? M would be the mass. R is the distance between your masses, right? I think it's best if you see pictures. And you should have the same as mine. You don't have pictures. It's the idea here is these rigid rotors, table 16.1. It's better just to look at the pictures. I should roll down a page number. Where are they? Okay, here they are. Page 464. Page 464. Okay. So they call them rigid rotors. And they calculated the I for you, right? Because some of these molecules are really complicated. So they calculated the moment of inertia for you. These equations are only good if what doesn't happen when these, because they're talking about rotating. Page 464. These equations and all these expressions in this table 16.1 are only good if what doesn't happen. The hint is rigid rotor. They got to be rigid, which means what isn't going to happen is these things are spinning. Imagine just one of these. Build it, put it together with styrofoam balls and sticks, right? And start spinning it. What's going to happen to it? It's going to fall apart. It's going to distort, right? I assume you build it stronger with springs maybe, right? And then they're going to start stretching. Well, that can't happen because these are what rotors? Rigid rotors. So it doesn't sound too, all right? It sounds like they're already assuming a lot here. But you must get pretty close answers with it. So that's why they do it, and it seems to be working for them.
What does it say, distance of?
Distance between blah, blah, blah. And it's really not that straightforward because look at the equations for some of these moments of inertia on these molecules. So I kind of left it just like that. It's easy if we just had two objects, right? Then it'd be the distance between the two, right? Like look at the diatomic, right? Number 1. But anything other than that, it gets uglier. So, okay.
It's amazing how smooth this coffee is compared to Polaroids.
Okay.
I wish I knew about it earlier, so I could have chewed them out of some more.
So, I'm just trying to look at it here. So you have, I think in general, was there 3? Usually I think of that R as the bond length, but that doesn't always work in this.
As a what?
As the bond length. And I'm trying to see, maybe that does work. Because if you look at all, it does work. So if you look at all these figures, all these rigid rotors, right, and look at their ugly equations, they have a big R in them, right? And if you look at the diagram, that big R is the bond length. So homework probably might involve these expressions with moments of inertia in them, maybe, and then they're after bond length, but I don't really quite remember what the homework's asking for. I don't think so, though, because I don't see any equations like that. So there's really not much to really talk about in there. Okay, I just typed this up for class because I was skimming through the homework and I saw this number 20. And I thought, well, how the heck I didn't even see this in the notes? And then I forgot about it. On page 460, they talk about the Boltzmann distribution. And all it is you take the number of molecules in, all right, just say number in, I can call it, just say the excited state. That's usually what they're talking about. And the number in the ground state. That ratio. So you can calculate ratios with the Boltzmann distribution. It's all about populations. That's all Boltzmann is really interested in. Populations of molecules and where they're at. So the ratio, and you can calculate their ratio. Really, I think this n usually belongs over there. That's how it usually looks like. The population in the excited state is going to equal the population in the ground state times e to the negative h nu over kt. But the book likes it this way, so I think that's how I did it. But so we've seen all these symbols before. H, Planck constant, frequency, Boltzmann constant, temperature. Okay. So as you raise the temperature, you get more and more in the excited state. Just, you can't stop it. So let's take a look at some of these questions then. See how ugly they are. It shouldn't be. We'll see. Let's see if I typed them up. Oh, I did. Good. Here's the first one. Calculate the ratio of Einstein coefficients of spontaneous and stimulated emission, A and B. The ratio, so they want A over B, right? For transitions with the following characteristics. Now I think what helps is, I don't know, do you guys have a big equation sheet for this? That would help to have that pulled out, if not have the notes. And then what also helps is when you see symbols like this, know what units they're talking about. And that really comes back to when I said know this table. Because there's 3 of them on there, right? Here's the units. I don't know if you can see it very well. right? Like, see how you have, can you erase? See how you have distance? Nanometers, meters, whatever. That's wavelength. Inverse centimeters, that's which symbol?
1 over lambda?
Oh, good. It could be 1 over lambda, or it could be, where lambda has to be in what units? Centimeters, if you're going to mess with that.
Yeah.
What's another symbol for 1 over lambda? Mu with a tilde, right? So know these, because otherwise you can't pick them out. Because the equations, the homework never gives you the variables. They just give you the units. What's the variable for hertz?
Frequency.
Frequency, and that's just that squiggly, that thing, right? Nu. So know those. Let's see. So they wanted to know, I lost it, A over B, and all they're giving you is the frequency, right? So there must be some way to work this out here. Where do they talk about these? Man, I messed everything up. Oh, here it is. Right? Just bring B over to the other side, and all you need is frequency. You can calculate this. Right? So would you put in 500 megahertz to get the right answer, or put in 500 times 10 to the... They said 500, 10 to the 6. That's the easiest way to do this stuff. Just know what all these, it's supposed to be big M, know what all these symbols represent. So just write in 500 times 10 to the 6. That's what your frequency will be. And you got to cube it times Planck's constant. Divided by the speed of light cubed. Just watch, make sure everything's in standard metric units, and you'll do good. Okay. Then they say 3 centimeter microwave radiation. Well, this must be what? Which variable? It's a unit of what? This is a unit of what? Length. This is a measurement of length. They're talking about light. So this must be which symbol? Mu with a tilde? No, that's 1 over centimeters. There's no R that we've talked about. Wavelength. Wavelength is distance, right? That's a way, right? That's distance.
So is that symbol the same as just a regular meter?
So this is the concept. The concept is wavelength is a distance. What are all the possible units of distance? Miles. 1 over distance. That's wave number. Does it have to be? It's not going to always be. Yeah, there's convention. There is convention. Nanometers, wavelength. Just because it's, you get nice numbers. But no, the concept is distance is wavelength. 1 over distance is wave number. 1 over what is frequency? 1 over time. 1 over time is frequency. So they tell you that 1 revolution takes 80 seconds. Right? So the frequency would be 1 for every 80 seconds, 1 over 80 seconds. So the point is, but these are the typical conventional units. So if you know, we'll go back to the question. If you know what wavelength is, well, you can calculate frequency. Right? How? How are they related? To the concept preview question. This one you should have burned in your head. That's the energy of a photon. Right? That's another one you should just have burned in your head. And why does this? The only way I can remember this is frequency is 1 over second. So this is the only way I can write it so that meters cancel. End up with 1 over second. Okay. So you can get it. So frequency is just c over lambda, so you can get it. What is the Doppler shifted wavelength of red traffic light? You're going to at 80 kilometers per hour. I guess you're going to need a monochromator to actually tell that it's not 660 nanometers anymore. But you're approaching that red stoplight. You probably need a Corvette to do that. Where is this Doppler stuff? I go too fast. Here it is, right? I should have wrote down all the numbers. I don't know which one we're talking about, right? So what would be the 80 kilometers per hour? What little symbol do you think? If you go and I can't show both equations at once here. If you look at the Doppler equation that we were referring to, the 80 kilometers per hour must be which symbol? Speed of the source, which is going to be little s. Okay. Let's see. So then, we need nu naught, right? So you can have to calculate nu naught out of that. Remember, frequency is c over lambda, so you can calculate it. All right. So then you can get your nu naught, and then you can get your frequency receding. But they want the Doppler shifted wavelength, so you got to convert that into wavelength. I bet it might be easier just to take a look at this, because frequency is c over lambda. So what you could do is just write c over lambda receding, c over lambda, right? The source, the initial, the 0. So then your c's cancel. Really, you just end up with a 1 over wavelength receding equals 1 over wavelength 1 over lambda 0, if you want to save yourself a couple steps, but that looks more complicated. Okay, but we're out of time, so come by, and I know it's a Friday, so it's kind of rough to ask questions, but you can ask questions after Monday, right? Even though you might have to turn in your work first. Just don't let a homework question slide. I think that's what killed on that last exam, right?
This one we just took.
You let